All right, so the next preliminary topics for stochastic processes is joint probability distributions, okay? So the outline for this review will include a brief introduction, joint and marginal probability distributions, conditional probability distributions. We also take a look at independence of joint probability distributions and also expectation of joint distributions, and finally on covariance and correlation coefficients, okay? So let's begin with the first session, which is going to be a brief introduction. So if x and y are two random variables, the probability distribution that defines their simultaneous behavior is called the joint probability distribution, okay? And the joint probability distribution of two random variables is sometimes referred to as the bivariate probability distribution or bivariate distribution of the random variables. So now let's begin with joint probability mass function. So what is joint probability mass function? So the function f of xy, which is equal to probability that x is equal to a particular value of x and y is equal to a particular value of y, is a joint probability mass function of the discrete random variables x and y if one, the joint probability mass function is non-negative for all values of x and y, and also the summation of the joint probability mass function is equal to 1. And thirdly, the cumulative density function for the joint PMF can be expressed in this form, okay? Probability that x is less than or equal to x and y is less than or equal to y, which can also be expressed in this form. All right, so these are the three main conditions that must satisfy the joint probability mass function. Now let's take a look at an example. The table below shows the joint PMF of x and y. The random variable x takes the values 0 and 1, while the random variable y takes the values 0, 1, and 2. Okay. So we have x here 0 and 1, and we have y here 0, 1, and 2. So what do we want to do? We want to find the probability that x is equal to 1 and y is equal to 2. And secondly, we want to find probability that the sum of the random variables will be greater than 1. Okay. So let's take a look at the solution for the first part. The probability that x is equal to 1, y is equal to 1 can also be expressed in this form, right, which is equal to 0. So how do we obtain a 0? Let me show you. So you can see that here x is 1, this is the value for 1, x1, and this is the value for x2, okay? So where they intersect, with the corresponding probability, okay? So 1 is here, and 2 is here. So the corresponding probability is 0. So that's why we have 0 here, okay? Now let's take a look at the second part, probability that x plus y is greater than 1. So let me show you here. So these are the possible values for x, and these are the possible values for y. So let's take a look at 0 plus 0. This one is less than 1, so we can't take the corresponding probability. 0 plus 1 is also less than 1, so we can't take this. But 0 plus 2 is greater than 1, so we can take the corresponding probability. Now let's take a look at this. 1 plus 0, right, is less than 1, so we can pick this. 1 plus 1 is greater than 1, so we can pick the corresponding probability. And 1 plus 2 is also greater than 1, so we can also pick the corresponding probability, okay? So this is how the solution will look like. To have this, and that. So we just pick the corresponding probabilities, okay? And once we sum, we obtain this. Very quite simple to do, okay? All right. So now let's take a look at the marginal probability mass function, okay? So what is marginal probability mass function? The individual probability distribution of a discrete random variable is referred to as the marginal probability mass function, okay? So basically we are talking about this. Let me show you. So there's the individual probability distribution for x, right? That's the row totals. The column totals is given as the marginal probability distribution for y, okay? So what you see here is displaying the marginal probability distribution for y, that's the column totals, right? And the row totals is given as the marginal probability mass function for x. Okay, so these are the individual probability distribution of a discrete random variable. Now, if x and y are two random variables with probability function f of x, y, then the marginal PMF of x is given by equation 1. So we have to sum over the region of y, okay? Similarly, the marginal PMF of y is given by equation 2, where we sum over the region of x, right? So we will take an example and see that this is very quite simple to do. So the table below gives the joint PMF f of x, y of the discrete random variables x and y. So here we have the joint PMF, and we want to find the marginal probability mass functions of x and y, okay? But there's a constant value here, k, which we have to find the value for k before we can compute the marginal PMF of x and y. So we will use the second condition, right? First, we find the value of k, and we are going to use the second condition under the PMF, joint PMF, to obtain k. So we know that once we sum all the joint probability mass function to be equal to 1, right? So we group like terms, we sum all the fractions, we obtain this. So we make k the subject and we obtain that, okay? So in place of k, we put 1 out of 6. So now we can compute the marginal PMF of x, okay? So we have to sum over the region of y, okay? So we hold the value of x constant, then we sum over the region of y. So we have 0, 3, 0, 4, and 0, 5. So we pick the corresponding probabilities, okay? So here we go. We do same for when x is 1. We have 1, 3, 1, 4, and 1, 5. So we pick the corresponding probabilities. Okay. So here we go. Then we do same for when x is 2, 2, 3, 2, 4, 2, 5. Okay. So we hold x constant or the value of 2 constant whilst the value of y will vary. Okay. So once we do that, we also obtain 1 out of 4. Very quite simple. So this is how the table will look like for the marginal PMF of x. And if you use a similar approach for y, you obtain this, okay? So this is what I mean for y3. We are going to sum over the region of x. So we have 0, 3, 1, 3, and 2, 3. So we get a column total for this. Then for y being 4, we have 0, 4, 1, 4, and 2, 4. So we sum this and we obtain the total. And we do same for 5, 0, 5, 1, 5, 2, 5. So we sum and we obtain this table here, okay? Very quite simple. So this is a try question. I will leave the solution in the description of this video so you can check it out. Please don't forget to subscribe if you have not. And for your notice, anytime you subscribe, there are no charges, okay? It is free of charge, so don't be scared to subscribe, okay? Thank you for watching.